Hey there! How's it going? Thanks for joining me today. Whether you're relaxing at home on your commute or winding down for the evening, I'm really glad you're here. Tonight, I want to tell you about something that happened in February 2024. Something that most people missed entirely, even though it changed how we understand our place in the universe. A visitor arrived, not from Mars, not from the outer reaches of our solar system, but from another star entirely. An object that had been traveling through the darkness between suns for longer than human civilization has existed. But here's the strange part. We almost didn't notice it at all. The discovery came on a clear night in Hawaii, where a network of automated telescopes called ATLAS scans the sky continuously. These telescopes weren't built to find interstellar visitors. They were designed to spot asteroids that might threaten Earth, those chunks of rock and ice that occasionally cross our planet's orbit. The system works tirelessly, imaging patches of sky every few hours, comparing each new image to previous ones, flagging anything that moved. On this particular night, the computers detected a faint speck. Just a point of light, dimmer than anything you could see with your naked eye, moving slowly against the background stars. The automated systems logged it, flagged it for review, and within hours, astronomers around the world were scrambling to their telescopes because the trajectory calculations revealed something impossible. This object wasn't orbiting the sun. It wasn't following an elliptical path like comets and asteroids do, bound by solar gravity into predictable loops. Instead, it was following a hyperbolic trajectory, a path that meant it was just passing through, a cosmic traveler that entered our solar system from interstellar space and would eventually leave again, continuing its journey into the galaxy beyond. Atlas, they named it. The 3I means it's the third interstellar object ever confirmed in human history. Think about that for a moment. Thousands of years of watching the sky, decades of sophisticated astronomical surveys, and we've confirmed exactly 3 visitors from beyond our solar system. 3 messengers from the vast spaces between stars. But what we don't know is far more fascinating than what we do. We know 3I Atlas is somewhere between 1 and 5 kilometers across, about the size of a small mountain. We know it's moving at approximately 70 kilometers per second relative to our sun. That's fast enough to cross the entire United States in less than 60 seconds. We know spectroscopic analysis shows it contains water ice, carbon monoxide, and organic compounds, the building blocks of chemistry we recognize. What we don't know is where exactly it came from. Working backward through its trajectory, astronomers can trace the path to a general region in the constellation Lynx, dozens of light years away. But which star, which planetary system ejected this wanderer into the cosmic void? That remains a mystery. There are hundreds of stars in that region of space. We don't know how long it's been traveling. Was it ejected 1 million years ago? 10 million? 100 million? The surface shows signs of cosmic ray bombardment and interstellar weathering. But dating that damage precisely is beyond our current capabilities. This object could have been drifting through the galaxy since before Earth had multicellular life, and here's what keeps me up at night. We don't know what else might be traveling with it. What stories does the ice contain, frozen in layers like tree rings? What chemical signatures from its birth system are locked inside? Could there be organic molecules complex enough to hint at biology in the star system it left behind? But tonight, I want to explore something even stranger. A thought experiment that pushes physics to its limits and reveals truths about the universe we're only beginning to understand. What if 3I Atlas wasn't the size of a mountain? What if it was as massive as Earth itself? The scale difference is almost incomprehensible. Earth's diameter is 12,742 kilometers. If 3I Atlas is, let's say, 3 kilometers across in reality, scaling it up to Earth's size means increasing the volume by approximately 64 million times. That's not just making something bigger, that's creating an entirely new category of object. something that's never been observed, something that exists in a gray zone between comet and planet, something that would challenge everything we think we know about how objects behave in space. Before we dive back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed, because tomorrow I've saved something extra special for you. When you scale something up that dramatically, physics doesn't just amplify, it transforms. A 3-kilometer snowball held together by the weak cohesion between ice crystals becomes a 12,000-kilometer sphere compressed by its own enormous gravity. A faint tail of sublimating ice becomes a cosmic lighthouse visible across the solar system. A cold, inert lump of ancient ice develops layers, internal heat, possibly even liquid water oceans hidden beneath kilometers of frozen crust. Comets, as we understand them, are fragile things. They're often described as dirty snowballs, loose aggregates of ice, dust, and rock, with more empty space than solid material. Their gravity is so weak you could jump off the surface and float away. They hold together through van der Waals forces, the same weak attraction that makes dust cling to surfaces. Planets are different. Planets are massive enough that their own gravity compresses them into spheres. The weight of the outer layers squeezes the interior, generating heat through compression, potentially creating differentiation where heavy materials sink and light materials rise. Planets have geology. They have internal structure. They're dynamic worlds where pressure and temperature create exotic states of matter. An Earth-sized comet would exist somewhere between these categories. And that's where things get truly mysterious. Here's what we can calculate. An object that size, even if composed primarily of ice and rock rather than Earth's iron-rich core, would have substantial surface gravity. Probably somewhere between 40 and 60% of Earth's gravity, depending on the exact composition and density. That's enough to hold itself together as a sphere. Enough that you'd feel weight standing on the surface. Enough to potentially retain an atmosphere, at least temporarily. But here's what we can't calculate with certainty. What happens to ice under those pressures? Normal ice, the kind in your freezer, the kind that makes up comets, exists at low pressures. But ice is strange. Unlike most materials, it has multiple high-pressure forms, exotic crystal structures that only exist under extreme conditions. Ice 7, for example, forms at pressures above about 20,000 atmospheres and remains solid even at several hundred degrees Celsius. Ice X, even more exotic, exists at pressures measured in millions of atmospheres, with properties that still puzzle physicists. At the core of an Earth-sized ice ball, pressures could reach hundreds of thousands of atmospheres. The ice there wouldn't be anything you'd recognize. And here's where it gets beautiful. Gravitational compression generates heat. All that weight squeezing down converts gravitational potential energy into thermal energy. The center of our hypothetical megacomet could reach temperatures of several hundred degrees Celsius. That's hot enough to melt ice into liquid water. Think about the paradox. A frozen world traveling through space, surface temperatures dropping below negative 200 degrees Celsius in the interstellar void, yet deep inside, protected by kilometers of insulating ice, a warm ocean could exist. Liquid water, heated by nothing more than the weight of ice above it, possibly mixed with dissolved minerals from whatever rock and dust the original comet contained. And wherever liquid water exists, even in the strangest environments, the question of life becomes unavoidable, but we're getting ahead of ourselves. We don't actually know if such an object can exist. We've never observed anything like it. The largest comets we've discovered are perhaps a few hundred kilometers across. Impressive, but nowhere near planetary scale. Theoretical models suggest that during the chaotic early formation of planetary systems, even massive objects can be gravitationally ejected. Recent simulations indicate that most star systems might actually eject more mass than they retain in planets. If that's true, the galaxy could be filled with orphan worlds. Rogue planets, massive comets, objects of every size, wandering the darkness between stars. Some estimates suggest there might be trillions of such objects drifting through the Milky Way at any given moment. A hidden population larger than the number of stars themselves, invisible to our telescopes, detectable only during the brief moments when they pass through a star system and catch enough light to be seen. Every few years, we spot one. Oumuamua in 2017, that strange, elongated object that tumbled through our solar system and sparked speculation about artificial origins because its acceleration couldn't be fully explained by known physics. Utwai Borisov in 2019, clearly a comet, behaving exactly as expected, but with chemical ratios that revealed it formed around a star with different conditions than our Sun. And now 3I Atlas in 2024, the latest messenger from the interstellar depths, 3 confirmed visitors in 7 years. But how many did we miss? How many passed too far away to detect or moved through regions of sky we weren't surveying, or were simply too dark to spot against the stellar background? The truth is we don't know, and that uncertainty is what makes this fascinating. Starting in 2025, that's changing. The Vera C. Rubin Observatory in Chile began full operations, equipped with the largest digital camera ever built and the ability to image the entire visible sky every few nights. Early projections suggested it might find 1 interstellar object per year. Recent statistical refinements based on the discovery rate so far now suggest 5 to 10 per year. Maybe more. Within a decade, we'll have enough data to answer fundamental questions. How common are interstellar visitors? What's the size distribution? Are they mostly pebbles and boulders? Or do massive objects regularly cruise between stars? How much variation exists in composition? And what does that tell us about planetary formation in different stellar environments? And perhaps, just perhaps, we'll spot one of the monsters. An object not kilometers but hundreds of kilometers across. Or even, however unlikely, something approaching planetary scale. If that happens, if we detect an Earth-sized object on an interstellar trajectory entering our solar system, everything I'm about to describe would shift from thought experiment to desperate urgency. Because such an object wouldn't just be scientifically fascinating, it would be gravitationally significant. Massive enough to perturb planetary orbits, massive enough to scatter asteroids and comets, potentially sending impactors toward the inner solar system, massive enough that its passage would leave permanent fingerprints on our cosmic neighborhood. The question becomes, what would such an encounter look like? Not the dry mathematical predictions of orbital mechanics, but the reality of it. What would you see in the sky? What would happen to the solar system's architecture? If you could somehow stand on the surface of this visitor, what would that impossible world be like? And deeper still, what would such an object teach us about the universe? About the connections between star systems? About whether life spreads through the galaxy on natural conveyances? Microbes frozen in ice, surviving million-year journeys and awakening in new solar systems? These questions sit at the edge of current knowledge, where established physics meets the unknown. We can calculate surface gravity and sublimation rates. We can model orbital perturbations and atmospheric dynamics. But we can't know with certainty what we'd actually find until we encounter such an object and study it directly. The real 3I Atlas, that 3-kilometer wanderer from another star, will teach us things about interstellar space and distant planetary systems. But scaled up to Earth size, it becomes something else entirely. A key that unlocks questions about planetary formation, the transport of material through the galaxy, the possibility of panspermia, and the hidden population of massive objects drifting in the spaces between stars. Over the next several chapters, we're going to explore every aspect of this scenario. We'll trace the journey from another star system across millions of years of interstellar drift to the moment of arrival in our solar system. We'll work through the physics step by step, showing how scaling changes everything. We'll stand on the surface and experience what such a world would be like. We'll watch it pass through our solar system, cataloging the chaos and beauty of the encounter. And we'll explore what it teaches us about the wider universe. Some of this we know, some of this we can calculate with confidence, and some of it remains genuinely mysterious, areas where our current understanding runs out and speculation begins, where the questions we can ask are more profound than the answers we have. That's the space I want to explore with you. The boundary between known and unknown, the place where science becomes most interesting, where each answer generates 10 new questions, where the universe reveals itself to be stranger and more connected than we imagined. Because here's the thing about 3I Atlas and objects like it. They prove something fundamental about our place in the cosmos. We're not isolated. Our solar system isn't a lonely island in an empty ocean. The galaxy is a web, with material constantly moving between the stars. Comets ejected from one system eventually enter others. Chemistry spreads. Organic molecules travel. And maybe, just maybe, life itself journeys between the stars on natural rafts of ice and rock, seeding worlds billions of kilometers apart. Every interstellar visitor is evidence of that connection. Everyone carries messages written in ice and stone, chemical signatures from alien star systems, clues about conditions light years away. We're learning to read those messages, to decode what the composition tells us about formation temperature and stellar chemistry, to understand what the trajectory reveals about galactic structure and the dynamics of planetary systems. But we've only just begun. 3 objects, 3 tiny samples from the vast population drifting through our galaxy. 3 pieces of a puzzle that might contain trillions of pieces. The story I'm about to tell you of an Earth-sized comet passing through our solar system is hypothetical. The real 3I Atlas is much smaller. The physics is real, the calculations are sound, but the specific scenario is a thought experiment designed to explore what's possible at the extreme edges of planetary science. Yet thought experiments have a way of becoming real. Before 2017, interstellar objects were a thought experiment. Now they're observed reality. Before exoplanet discoveries, worlds around other stars were speculation. Now we've confirmed thousands. The universe has a habit of being stranger than we imagine, of containing phenomena we hadn't predicted, of surprising us with its diversity and complexity. So as we explore this impossible comet, remember, we're not just playing with numbers. We're training ourselves to recognize possibilities, building the conceptual framework to understand what might actually exist out there, preparing for discoveries that haven't happened yet, but almost certainly will, because the universe is vast. The galaxy contains 200 billion stars, each potentially surrounded by planetary systems, each system potentially ejecting material into interstellar space. Over billions of years, that adds up. The spaces between stars are populated with refugees from countless systems, a hidden population we're only beginning to detect and characterize. Some are small, like the real 3I Atlas. Some might be massive, the orphans of planetary formation, worlds that never found a stable orbit and instead were flung into eternal wandering. And somewhere in that population, at the tail end of the size distribution, there might be objects that blur the line between comet and planet. Ice worlds massive enough to have internal oceans and active geology, yet still containing the volatiles that make comets spectacular. Natural hybrids we've never seen because they're rare, or because we haven't looked carefully enough, or because we're only now developing the tools to spot them. The next decade will tell us. As detection systems improve and catalogs grow, we'll map the population of interstellar travelers. We'll discover whether Earth-sized wanderers exist naturally. We'll potentially find objects that challenge our categories and force us to expand our understanding of what's possible. And when we do, when the first truly massive interstellar visitor is detected, when astronomers calculate its trajectory and realize it's big enough to matter gravitationally, we'll need to understand it quickly. Its approach timeline, its composition, its effects on our solar system, whether it poses any risk, and what opportunities it presents for study. That's why we explore these scenarios now. Not because we expect them tomorrow, but because the universe doesn't consult our expectations. It does what physics allows, and physics allows for objects far stranger than we've yet imagined. So let's begin the journey. Let's take that small, real comet, 3I Atlas, visitor from another star, and scale it up to something unprecedented. Let's watch what happens when gravity and chemistry and thermodynamics interact at planetary scales in an object that shouldn't exist according to our current experience, but might exist somewhere out there in the galaxy, waiting to be discovered. Let's explore what happens when the alien visitor isn't just a messenger, but a world unto itself. The adventure starts with understanding where such an object would come from, how it would survive the journey between stars, and what triggers the transformation when it finally enters a new solar system and feels the warmth of an alien sun for the first time in millions of years. That story begins billions of years ago, in a planetary system nothing like ours, where the architecture of worlds was still being determined and the fates of countless objects hung in the balance of gravity and chance. The star system where our story begins no longer exists. At least, not in the form it once had. 4 billion years ago, maybe more, a young sun blazed in a corner of the galaxy dozens of light years from where Earth would eventually form. Around it, a disk of gas and dust swirled, condensing into worlds. Giant planets coalesced in the outer regions, their massive gravitational fields sweeping up material and clearing paths through the debris. Smaller bodies, ice-rich planetesimals, formed beyond them, in the cold outer reaches where water froze solid and carbon compounds remained locked in ice. This is where our object was born, not as the wanderer it would become, but as one piece among trillions in a vast reservoir of comets surrounding the infant star system. A cosmic snowball a few kilometers across, composed of ice that condensed directly from the protoplanetary nebula, mixed with dust grains and rocky fragments. Its chemistry recorded the temperature and composition of that long-ago star system. Ratios of water to carbon monoxide, abundances of organic molecules, isotope signatures that would serve as fingerprints billions of years later. But here's what we don't fully understand: the exact mechanism of ejection. We know it happened. The trajectory calculations for 3I Atlas work backward to interstellar space, and before that, to some distant stellar neighborhood. We know such ejections must be common. Current models suggest that for every kilogram of material retained in planets, several kilograms get flung into interstellar space during the chaotic formation period. Early planetary systems are violent places where gravitational interactions between forming worlds regularly exceed escape velocity. What we don't know is the specific sequence of events. Was our object nudged inward from its original orbit by a passing giant planet, accelerated through a series of gravitational assists until it reached escape velocity? Did it witness a close encounter between two massive worlds whose gravitational dance flung hundreds of smaller bodies into interstellar trajectories? Or was it part of a resonance cascade, a domino effect where one ejection triggered others in a chain reaction of orbital destabilization? The difference matters because it tells us about the architecture of that alien system. Different ejection mechanisms produce different velocity distributions, different preferred directions, different probabilities for various object sizes. By studying enough interstellar visitors and mapping their velocities and compositions, we could potentially reconstruct the typical architecture of planetary systems across the galaxy. But with only 3 confirmed objects, we're still guessing. What we can say with confidence is this: the moment of ejection was violent and final. Picture the scene. Our comet, having orbited its birth star for perhaps tens of millions of years in a stable orbit, suddenly encounters a giant planet. The planet's gravity accelerates the comet inward toward the star, but the trajectory is precise enough that instead of colliding with the planet or falling into the star, the comet whips around the planet's backside, a gravitational slingshot that adds the planet's orbital velocity to the comet's own speed. 70 kilometers per second, maybe 80. Fast enough that the star's gravity can no longer hold it. The comet races outward, climbing away from the star, but this time it doesn't slow down and fall back. It has enough energy to escape entirely. Behind it, the star it has orbited since formation grows dimmer. Ahead lies only darkness. The trajectory carries it up and out of the planetary system, through whatever outer disk or shell of comets still surrounds the star, and finally into interstellar space proper. The transition is gradual. There's no boundary marker, no sign saying, now leaving star system. But at some point, perhaps a light year out, perhaps several, the star's gravity becomes negligible. Solar wind fades to nothing. The object enters. True interstellar space. That vast emptiness between stars. And here's where the mystery deepens. What happens during the journey? The duration alone is staggering. If 3I Atlas traveled from a star system 40 light-years away, a conservative estimate based on the trajectory, and moved at 70 kilometers per second the entire time, the journey would take more than 170,000 years. If the origin is farther, or if the initial velocity was lower and gravitational interactions with other stars modified the trajectory, the journey could span millions of years, perhaps tens of millions. During that time, the object experiences conditions unlike anything in a planetary system. The temperature drops to within a few degrees of absolute zero, around negative 270 degrees Celsius. No sunlight warms the surface. No stellar wind affects it. The only energy input comes from cosmic rays, high-energy particles, produced by supernovas and other violent cosmic events that constantly bombard the surface. Those cosmic rays gradually change the chemistry of the ice. They break molecular bonds, creating free radicals that recombine in new ways. They can transform simple molecules into more complex ones. Over millions of years, this cosmic ray processing might create an outer layer with chemistry different from the pristine interior, a rind of radiation-altered material that records the duration of interstellar exposure. But we don't know the details. We've never sampled interstellar ice directly. The surfaces of Oumuamua and 2I Borisov and 3I Atlas have all been observed only from vast distances through spectroscopy that reveals bulk composition but not fine structure. What exotic molecules might cosmic ray chemistry produce? How deep does the altered layer extend? Could the processing create prebiotic compounds, amino acids, nucleobases, lipids, that might later seed chemistry in whatever star system the object eventually enters? These questions remain unanswered. We have theories, simulations, laboratory experiments that expose ice to radiation under interstellar-like conditions. But theory and reality don't always match. The universe has a way of surprising us with complexity we hadn't anticipated. The journey itself follows not a straight line, but a curve through the galaxy. The Milky Way rotates, carrying everything with it, and stars move relative to each other through the galactic disk. Our wanderer follows its own trajectory, influenced by the gravitational field of the galaxy as a whole, but not bound to any particular star. It's a free agent, a cosmic nomad, following whatever path its ejection velocity and subsequent gravitational nudges from distant stars have determined. Occasionally, perhaps once every million years, perhaps more often, it passes through regions of slightly higher density, molecular clouds, those vast nebulas where new stars form. The object might accumulate a thin coating of interstellar dust or experience slightly different radiation environments. These passages leave subtle signatures, variations in surface, chemistry that could theoretically be read like geological strata if we could examine the object up close. Before we continue, I want you to imagine something. Picture the loneliness of it. A single object, a few kilometers of ice and rock, drifting through the void. The nearest stars are light years away, so distant they appear as dimensionless. Points of light, indistinguishable from the stars behind them. No planets, no moons, no other objects except the occasional extremely rare encounter with another ejected body or a microscopic dust grain. For the equivalent of 1,000 human lifetimes, nothing changes. The object simply drifts, frozen, silent, dead to all appearances. But here's what we're learning. Those wanderers might not be as dead as they appear. Recent studies of cosmic ray effects suggest that radiation chemistry could potentially sustain slow chemical reactions even in deep freeze. Not metabolism as we'd recognize it. Nothing living could function at those temperatures. But chemical evolution, the gradual complexification of molecules, the creation of new compounds that wouldn't form in warmer environments. Interstellar. Ice might be a laboratory for exotic chemistry we can't replicate on Earth, processes that occur only over millions of years in radiation-soaked conditions. And then there's the question that keeps astrobiologists awake at night. Could life survive the journey? Not complex life. Nothing could function metabolically at near absolute zero, but microbes in a state of suspended animation, frozen so thoroughly that molecular motion effectively stops. On Earth, we've revived bacteria from million-year-old ice cores. We've found organisms that survive years of vacuum exposure in space experiments. The mechanisms exist: proteins that prevent ice crystal damage, cellular systems that enter dormancy so complete they're barely distinguishable from death. If a comet was ejected from a star system with active biology, a planet with oceans and ecosystems, and if that ejection was violent enough to spray material from the planet into space, some of that material might include microbes, frozen instantly, preserved in the deep freeze of interstellar space, potentially viable for millions of years, waiting for the warmth of a new star system to awaken them. We don't know if this happens. We have no confirmed cases of panspermia, no proof that life spreads between star systems on natural objects, but the possibility exists within known physics and biology, and interstellar objects like 3I Atlas are the mechanism by which it could occur. The journey continues for time frames that dwarf human history. Empires rise and fall on Earth, which doesn't exist yet, while our wanderer drifts through the dark between stars. The galaxy rotates fractionally, stars move in their orbits, and gradually, statistically, inevitably, the wanderer's path begins to curve toward a new star. Not intentionally. There's no guidance system, no purpose to the trajectory, but space is vast and stars are numerous. Eventually, any object drifting through the galaxy will pass near enough to a star for that star's gravity to become significant. For our object, that star is ours, the Sun. The approach takes centuries, even after the Sun's gravity becomes the dominant influence. At first, the effect is subtle, a slight bend in trajectory, a gradual acceleration toward this new gravity well. The object is still far beyond the orbit of Neptune, still in the realm of the Kuiper Belt and scattered disk, that outer frontier of our solar system, where the sun's light is faint and temperatures remain deeply frozen. But inward it falls, slowly at first, then faster as gravity accumulates. The sun grows brighter. Ahead, no longer a point among points, but noticeably more luminous. Not yet bright enough to warm the ice, but bright enough that if anything could observe, it would recognize this star as special, different from the background. A destination rather than just another light. And then, crossing some invisible threshold, perhaps around 30 astronomical units out, in the region of Neptune's orbit, the first changes begin. The sun's radiation, still faint but present, starts to affect the surface. The outermost layer, that rind of cosmic ray-altered chemistry, begins to sublime. Molecules gain enough energy to break free of the ice matrix. Gas escapes, carrying dust with it. the object develops its first faint coma, that cloud of gas and dust surrounding the nucleus. It's barely detectable, but it's there. After millions of years of dormancy, the ancient ice awakens. This is where we pick up the story in real time. In February 2024, when automated telescopes in Hawaii capture that faint glow and recognize it as something moving against the stars. But by then, the transformation has already begun. The interstellar wanderer is becoming an active comet again, ice sublimating as it hasn't since it left its birth system millions of years ago. The spectroscopy begins immediately. Telescopes around the world point toward this visitor, splitting its light into component wavelengths to read the chemical signatures. And this is where things get fascinating, because the chemistry tells stories. The ratios of different ices reveal formation temperature. Too much carbon monoxide relative to water suggests formation in an especially cold region. Organic molecules, the complex carbon-based compounds that form in protoplanetary disks, reveal the metallicity of the birth star and the chemistry available during formation. Isotope ratios, especially deuterium to hydrogen, indicate the specific conditions in that long-ago nebula. For 3I Atlas, the chemistry is mostly familiar. Water ice dominates, with carbon monoxide and carbon dioxide mixed in. Organic compounds appear in the spectrum, simple ones like formaldehyde and methanol, more complex ones hinted at but not fully resolved. The ratios are close to what we see in our solar system's comets, but not identical. There are differences, subtle but real, that suggest the star system where this formed had slightly different conditions than the nebula that birthed our sun. What those differences mean, we're still deciphering. Does a higher ratio of one ice to another indicate formation farther from the star? Or does it reflect different chemistry in that star's protoplanetary disk, perhaps because the star had more or fewer heavy elements than our sun? These are questions we're only beginning to answer with 3 data points. But here's what intrigues me most, what we can't detect from spectroscopy alone. The interior chemistry remains hidden. We see only the surface, the outer layers sublimating into space. Whatever lies beneath, protected from direct sunlight, remains unknown. If the interior contains chemistry created by cosmic ray processing, we won't see it until the object passes close enough to the sun that deeper layers begin to sublime. If there are pockets of exotic ices or unusual minerals concentrated during formation, they're invisible to current instruments, and if, however unlikely, there's any biological material preserved in the ice, frozen since ejection from an alien biosphere, we have no way to detect it without direct sampling. Spectroscopy can identify organic molecules, but it can't distinguish between abiotic organics and the complex organized chemistry that indicates life. For that, we'd need to land on the object, drill into it, examine samples under microscopes, look for cellular structures or biomolecules with the telltale signatures of biological processing. We're nowhere close to that capability for interstellar visitors. They move too fast, appear too suddenly, and leave too quickly for current mission architectures to intercept them. By the time 3I Atlas was confirmed as interstellar, it was already inbound, weeks away from closest approach to the sun, moving at velocities that would require enormous fuel expenditures to match. We watch it pass, we study it remotely, and then it leaves, returning to the interstellar dark, and we're left with data and questions, and the hope that next time we'll be more prepared. But imagine if the scale was different. If instead of a few kilometers snowball, we were watching something massive approach, something Earth-sized, with enough gravitational presence that its approach would be detected years in advance, giving time to plan missions, to coordinate observations, to prepare for an encounter that would be historic, not just scientifically, but civilizationally. That's the scenario we're going to explore. Because scaling up doesn't just make things bigger, it transforms them fundamentally. And an Earth-sized comet arriving from interstellar space would be something the universe has perhaps created, but we've never witnessed. The journey from another star, across millions of years of cosmic isolation, would be the same. The chemistry would be the same in principle. But the consequences of that arrival, what happens when something that massive begins to warm up, to sublime, to interact gravitationally with our solar system, would be unprecedented. In the next chapter, we're going to scale up. We're going to take everything we know about how comets work, about how ice behaves under pressure, about how gravity shapes worlds, and we're going to push it to the extreme. We're going to create, in thought if not reality, the most impossible comet imaginable, and watch what physics demands when you make something that big, because that's where the real mysteries begin. In the gap between small comet and ice planet, there's a whole range of objects we've never studied. Objects that might exist out there in the interstellar population, rare but possible, waiting to be discovered. And if we ever find one, everything we're about to explore will shift from thought experiment to urgent necessity. There's a moment in physics where quantity becomes quality, where making something bigger doesn't just amplify what you have, it creates something entirely new. A candle flame and a forest fire are both combustion, but they behave according to different rules. A puddle and an ocean are both water, but the ocean has currents, tides, and climate systems that don't exist in the puddle. This is what happens when you scale up a comet. Picture holding a snowball. It fits in your palm, maybe the size of a baseball. The ice crystals cling together through weak molecular forces, Van der Waals interactions, the same forces that make dust stick to surfaces. Drop it and it might crumble. Throw it, and it might compress slightly from impact. But fundamentally, it's a simple object. Frozen water loosely packed, held together by forces barely stronger than static electricity. Now imagine that snowball growing. At twice the size, basketball-sized, it's still essentially the same. The forces holding it together are the same. The ice crystals have the same structure. You could still crush it in your hands if you wanted to, though it would take more effort. Keep going. At 10 times the original size, you have a snowball the size of a small car. Now the weight matters. The bottom is compressed slightly by the mass above it, but only slightly. It's still fundamentally a loose aggregate. You could tunnel through it with your hands given enough time. At 100 times the original size, a snowball as big as a large building, something begins to change. The weight of the outer layers creates real pressure at the center. Tens of atmospheres, maybe. Not enough to alter the ice's crystal structure, but enough that the ice at the core is noticeably denser than the ice at the surface. The object has begun to differentiate, if only slightly. At 1,000 times the original size, we're approaching a kilometer across. Now we're in comet territory, and the physics shifts significantly. The self-gravity becomes meaningful. The object naturally forms itself into a rough sphere because gravity pulls everything toward the center of mass. The pressure at the core reaches hundreds of atmospheres. The ice there is compressed, transformed from the fluffy, porous structure of the surface into something denser and more solid. But here's where it gets really interesting. Keep going. At 10,000 times the original size, we're talking about objects 10 kilometers across. Large comets, the kind that make spectacular passages when they approach the sun. The core pressure reaches thousands of atmospheres. The ice undergoes the first phase transitions, beginning to form high-pressure structures that don't exist at the surface, and gravitational heating becomes significant. The weight of all that ice above compresses the core, and compression generates heat. Not much heat, not enough to melt anything, but measurable. The deep interior might be tens of degrees warmer than the surface, sustained by nothing more than the slow, steady compression of gravity. And now comes the leap that takes us into genuinely unexplored territory at Earth size, 12,742 kilometers in diameter. We've scaled up by approximately 4,000 times from a large comet. But the volume has increased by the cube of that, 64 million times more material. And mass scales with volume. So we're talking about an object with tens of times more mass than any comet we've observed. The physics transforms completely. First, the gravity. Surface gravity depends on mass divided by radius squared. An Earth-sized ball of ice and rock, let's say with an average density about 40 to 50% of Earth's density would have surface gravity somewhere between 40 and 60% of Earth's pull. That might not sound like much, but it's the difference between floating away and being held firmly to the ground. It's enough gravity to reshape the object into a perfect sphere through hydrostatic equilibrium. It's enough to potentially hold an atmosphere, at least temporarily, but the real transformation happens inside. At the center of our Earth-sized comet, the pressure becomes enormous. Not Earth core enormous. Ice and rock don't weigh as much as Earth's iron-nickel core, but still immense. Calculations suggest central pressures around several 100,000 atmospheres. That's higher than the deepest ocean trenches on Earth, higher than the pressure inside Jupiter's atmosphere, where it transitions from gas to liquid, and ice under those pressures doesn't behave like the ice, normal ice, the stuff in your freezer. What scientists call ice exists only at low pressures. At higher pressures, water molecules reorganize into different crystal structures, each with its own properties and characteristics. We've discovered more than 18 different phases of ice, most of which only exist under extreme conditions. At our megacomet's core, the ice would transform into Ice 7, a cubic crystal structure that forms at pressures above about 20,000 atmospheres. Ice 7 is denser than normal ice. It actually sinks in liquid water, unlike the ice you're familiar with. And bizarrely, it remains solid at temperatures well above water's normal boiling point. You can have Ice 7 at several hundred degrees Celsius, held solid purely by pressure. Deeper still, approaching the very center where pressures peak, the ice might transition to Ice X, an even more exotic form, where hydrogen atoms are squeezed so close to oxygen atoms that they share electrons in unusual ways. Ice X has properties we're still trying to understand fully: its electrical conductivity, its optical properties, its thermal behavior all differ from normal ice in ways that defy intuition. But here's the paradox that makes this scenario so fascinating. All that compression generates heat. Gravitational potential energy converts to thermal energy as material settles under its own weight. It's the same process that keeps Earth's interior hot billions of years after formation. For our megacomet, the calculations suggest the core could reach several hundred degrees Celsius. Maybe 300, maybe 500. The exact number depends on composition, heat flow, and thermal properties we can only estimate. But here's what we know for certain: that's hot enough to melt ice into liquid water. Think about the strangeness of this. The surface of this object exposed to space sits at negative 200 degrees Celsius or colder, frozen solid, as dead and inert as any comet you've seen. But travel down through kilometers of ice, through the transition zones where Ice gives way to Ice 7, through layers compressed and transformed by the weight above, and eventually you reach a boundary where temperature climbs above 0 Celsius and ice melts. Deep inside this frozen world, protected by kilometers of insulating ice above, an ocean could exist. Liquid water, heated by nothing more exotic than gravity itself, possibly mixed with dissolved minerals and salts from whatever rocky material the original comet contained. An ocean that has never seen sunlight. An ocean that exists purely because an object became massive enough for its own weight to generate the heat necessary to melt its own interior. But here's what we don't know, and it's a significant gap in our understanding. Can such an object actually form? We've never observed anything like it. The largest comets we've confirmed are perhaps a few hundred kilometers across. Substantial, but still orders of magnitude smaller than Earth. Theoretical models suggest that during planetary system formation, even large objects can be ejected. Simulations show that some star systems might eject planet-sized bodies during the chaotic gravitational interactions of early formation. But simulations aren't reality. Models make assumptions. about how often close encounters occur, about the efficiency of gravitational scattering, about whether large icy bodies can hold together during violent ejection events. We don't know if an Earth-sized comet could survive the ejection process intact, or if the gravitational stresses would tear it apart before it reached interstellar space. We don't know if such objects, even if they form, remain stable over millions of years of interstellar drift. Would internal heat create convection patterns that gradually differentiate the object, concentrating rock at the center and ice at the surface? Would the phase transitions create structural weaknesses that cause fracturing? Would cosmic ray bombardment over millions of years alter the surface in ways that affect the object's evolution? These are genuine unknowns. We have theories, but theories in this regime are educated guesses at best. The universe might allow Earth-sized comets, or it might impose some upper limit we haven't identified. We won't know until we either observe one or develop much more sophisticated models of planetary system dynamics. Before we go further, let me paint you a picture of what happens as this object approaches the Sun. Remember, this is an interstellar visitor, fresh from millions of years in the deep freeze between stars. Its surface has been at near absolute zero temperatures for longer than human civilization has existed. The ice there is ancient, radiation-scarred, possibly covered with a thin layer of organic compounds created by cosmic ray chemistry. But now, sunlight begins to warm it. At first, the effect is minimal. Beyond Neptune's orbit, 30 astronomical units from the Sun, the sunlight is faint, carrying less than 0.1% of the energy it delivers to Earth. But it's enough. Molecules on the surface gain energy. The most volatile compounds, carbon monoxide, which sublimates at -205 degrees Celsius, begin to escape. A faint atmosphere forms. Incredibly thin, thinner than the best vacuum we can create in laboratories on Earth, but present. Gas molecules escaping from the surface create a tenuous envelope around the object. This is the beginning of the coma, that cloud of gas and dust that makes comets visible. But with an Earth-sized object, the scale changes everything. A normal comet a few kilometers across might have a coma extending thousands of kilometers. The coma is big relative to the nucleus, but in absolute terms, it's small. A megacomet, with a surface area millions of times larger, can produce sublimation across its entire sunlit hemisphere simultaneously. The coma becomes enormous, potentially millions of kilometers across, larger than the Sun itself. And the gas production rate, even at these vast distances where sublimation is slow, could reach thousands of tons per second, purely through the sheer size of the active surface. As the object moves inward, crossing Uranus's orbit, then Saturn's, the warming accelerates. Water ice begins to sublime. First the topmost layer, just molecules thin, but gradually working deeper as solar heat penetrates. Carbon dioxide creates jets where it concentrates in pockets beneath the surface. The gas pressure building until it erupts through weak points. By the time it crosses Jupiter's orbit, 5 astronomical units from the Sun, the transformation is dramatic. The sunlit side reaches temperatures around -150 degrees Celsius. That's cold by Earth standards, but it's warm enough for vigorous sublimation. The surface literally evaporates, ice turning directly to gas at rates that would be measured in meters per year. And here's where the megacomet does something impossible for its smaller cousins. It holds onto some of that gas. The gravity, 40 to 60% of Earth's, is strong enough to retain heavy molecules. Carbon dioxide has a molecular weight of 44. Water vapor is 18. These are heavy enough that at the temperatures we're discussing, many molecules don't reach escape velocity. They sublime from the surface, but instead of immediately flying off into space, they enter a temporary atmosphere. The atmosphere would be thin by Earth standards, perhaps a few millibars at most, similar to the pressure in Mars's atmosphere, but it would be real, and atmospheres create weather. On the day side, sublimation continuously feeds gas into the atmosphere. On the night side, remember this object probably rotates with a period of hours or days. The temperature drops precipitously. Gas freezes out, snowing back down to the surface. You'd have a cycle. Sublimation during day, redeposition during night, with wind patterns developing between the hot day side and cold night side. Clouds could form in this atmosphere. Not water clouds like Earth's, but carbon dioxide clouds, or water ice crystal clouds in the coldest regions. The sunsets, seen from the surface, would show atmospheric phenomena. Halos, light scattering, possibly even lightning from triboelectric effects. As ice particles collide in sublimation jets, the tail becomes spectacular. Solar wind, that stream of charged particles flowing out from the sun, pushes gas and dust away from the sun, creating the classic comet tail. But our megacomet produces so much material that the tail could extend beyond Mars's orbit when the object reaches perihelion. From Earth, this would be visible as a structure dominating the night sky. Not a point of light, not even a smudge, but an elongated bridge of glowing gas stretching across dozens of degrees of sky, bright enough to cast shadows, bright enough to be visible even in light-polluted cities. A cosmic spectacle unlike anything witnessed in human history. But we haven't talked about the most intriguing possibility yet. What happens inside? The subsurface ocean, if it exists, would be isolated from the surface by kilometers of solid ice. But the vigorous sublimation at the surface creates pressure differentials. As ice sublimes away, the surface level drops. The weight pressing down on the interior decreases slightly, and in any place where fractures or weak zones exist, pressure from below could find release. Imagine a fissure extending from the surface down toward the ocean layer. As surface sublimation reduces the overburden pressure, water from the ocean, liquid water under enormous pressure, finds a pathway up. It ascends through the fracture, driven by the pressure differential. As it rises, the pressure decreases, and eventually it reaches levels where it flash freezes or explosively vaporizes. You'd get cryovolcanism on a planetary scale. Geysers erupting not just water vapor but liquid water, which freezes instantly in the cold of space into ice particles that rain back down across hundreds of kilometers. Active ice volcanoes marking the surface with fresh deposits of erupted material. Vents that connect the hidden ocean to the surface, however briefly, before freezing shut again. These eruption sites would be windows into the interior. They'd bring up dissolved minerals, organic compounds concentrated in the ocean, possibly even mineral precipitates formed at the rock-water interface deep inside. If there were any biological material, and that's a huge if, these would be the places where it might be detected from the surface. But here's what keeps me fascinated. We don't know what else might happen. The thermal gradients, extreme cold at the surface, relative warmth at depth, create convection patterns in the ice. Different ice phases have different densities. Ice 7 is denser than Ice I. Does it sink? Do you get convection cells in solid ice, creeping slowly over millions of years, cycling material between surface and depth? The tidal forces from passing near the sun or planets would flex the interior. This flexing generates additional heat through friction. It might maintain liquid regions that would otherwise freeze. It might create seismic activity, ice quakes propagating through the crust, adjusting the structure as internal pressures shift. The rotation creates Coriolis forces that affect atmospheric circulation and potentially even patterns in the sublimation. Different longitudes experience different solar heating as the object rotates. Does this create zones, like Jupiter's bands, where sublimation is more or less active? Every answer generates new questions. Every calculation reveals another layer of complexity. We're dealing with an object that doesn't fit our existing categories. Too big to be a comet as we understand comets. Too icy to be a rocky planet. Too volatile rich to be a stable ice world, like some of the outer solar system moons. It exists, hypothetically, in a gap in our knowledge. And gaps like that are where the most interesting discoveries happen. In the next chapter, we're going to stand on this impossible world. We're going to walk its surface, explore its canyons and ice cliffs, watch the sublimation happen in real time, and try to understand what it would actually be like as a place, rather than as a set of physics equations. Because that's where thought experiments become real. When you can imagine being there, experiencing it directly, the abstractions of pressure and temperature and gravity transform into something tangible. And in that tangibility, you start to see not just what this object is, but what it means. The landing craft descends through darkness toward a surface that shouldn't exist. You're strapped into your seat, watching through the viewport as thrusters fire in precise bursts, adjusting trajectory, compensating for the gravity that pulls steadily at the craft. Not Earth-normal gravity, but enough that the descent feels controlled, almost gentle. Your inner ear tells you which way is down. That alone is remarkable. On a normal comet, the kind humans have actually visited, there is no down. Gravity is so weak that astronauts would float, barely tethered to the surface by forces weaker than a gentle breeze. But here, you feel weight. Real weight. The altimeter counts down 500 meters. 300. 100. The surface resolves in the landing lights. Not smooth, not flat, but textured with features your brain struggles to process. Ice formations like nothing on Earth. Structures carved by sublimation and thermal stress and the slow creep of material under its own weight. 50 meters, 20, 10. The thrusters fire hard, breaking the final descent. Impact. The craft settles with a crunch of ice beneath the landing pads. And then silence. You're on the surface of an Earth-sized comet, a visitor from another star, an object that exists in the gap between world and wanderer. The first thing you notice when you step outside is the gravity, 60% of Earth's pull, enough that walking feels natural, though every step launches you higher than you'd expect. Jump, and you hang in the air for just a moment longer than feels right. Drop something, and it falls but slowly enough that you could almost catch it mid-descent. The landscape stretches before you in shades of white and grey and pale blue. Ice, endless ice, but not the smooth skating rink surface you might imagine. This is ancient tortured ice that has experienced temperature extremes over millions of years. The surface is chaos. Crevasses split the ground, some narrow enough to step across, others wide enough to swallow buildings. They descend into darkness, their depths unknowable without instruments. Some formed from thermal contraction as the object cooled in interstellar space. Others opened recently, within days perhaps, as the warming from the approaching sun creates expansion stresses. Between the crevasses rise pressure ridges, places where ice sheets have collided and buckled upward like tectonic plates on Earth. These formations reach tens of meters high, jagged walls of ice tilted at impossible angles, some transparent enough that light penetrates them, others clouded with trapped air bubbles and dust, and everywhere impact craters. Small ones pockmark the surface, micrometeorite strikes that occurred during the millions of years of interstellar journey. Larger ones, perhaps from encounters during the object's time in its birth system, or from debris captured during its passage through our solar system, create bowl-shaped depressions partially filled with frost. The horizon is closer than on Earth. This world curves at the same rate, but you're standing on accumulated ice layers that might be kilometers above the mean radius. The curvature is visible, a gentle arc that reminds you this is a world, not a flat landscape extending forever. Above, the sky is black. Not the blue-black of high altitude on Earth, but the pure, absolute black of space. Stars blaze with a clarity impossible through Earth's atmosphere, unwavering points of light scattered across the vault of heaven. And they're wrong. The constellations are familiar but subtly distorted because you're moving through space at 70 kilometers per second. The parallax shift is tiny but measurable. Stars directly ahead appear slightly compressed together, while stars behind are spread slightly apart, but the most dramatic feature dominates one portion of the sky. The sun. You're near perihelion, closest approach, at perhaps 1.5 astronomical units. The Sun appears smaller than from Earth, roughly the size it looks from Mars. But even at this distance, it's intensely bright. Your visor automatically darkens to protect your eyes. The light it casts is different from sunlight on Earth, colder somehow, more stark, throwing razor-sharp shadows across the ice, and you can see the response of the surface to that light. Gas rises from the ground like morning mist. But this isn't water vapor condensing in cool air. This is ice sublimating directly from solid to gas, molecules gaining enough energy from solar heating to break free from the ice lattice and escape into space. The effect is subtle at first, a slight haziness near the surface, a shimmering in the sunlight where the density gradient bends light. But watch for a few minutes, and you begin to see the activity. Small jets erupt from cracks in the ice, places where pressure has built up beneath the surface and finds sudden release. The jets shoot upward, carrying dust and ice crystals that catch the sunlight and glow. Most of the material falls back down, following parabolic arcs under the world's gravity, but the fastest particles, those moving above escape velocity, stream away into space, feeding the tail. The tail. From here, standing on the surface, you can't see it directly. It stretches away on the anti-sunward side, millions of kilometers of gas and dust pushed back by solar wind. But you can see its beginning, the gas production happening right beneath your feet. The dust being lofted into the thin atmosphere, the start of the process that creates that spectacular cosmic banner visible from Earth. The temperature gauge in your suit reads -100 degrees Celsius. Cold by Earth standards, but warm for this object. In interstellar space, the surface temperature hovered around -270 degrees, just a few degrees above absolute zero. The Sun's warmth, even at this distance, represents a heat wave that's driving massive changes. You check the atmospheric pressure reading, 3 millibars. That's less than 1% of Earth's atmospheric pressure at sea level, roughly equivalent to the altitude where Earth's atmosphere fades into space. But it's real. This temporary atmosphere is thick enough to carry sound, faintly but detectably. You can hear the hiss and crackle of sublimation, the pops as ice fractures under thermal stress, even the whisper of wind as gas flows from the dayside toward the terminator. Wind on a comet. The concept seems absurd, but here it is, atmospheric circulation driven by the temperature, differential between the sunlit hemisphere and the shadowed regions. The wind is weak, barely a breeze, but measurable. Dust devils form occasionally, tiny vortices of ice crystals spiraling upward before dissipating. But here's what you don't know, and what fills you with a mixture of excitement and unease. What lies beneath? Your instruments can penetrate the ice to a certain depth. Ground-penetrating radar shows structure down to a few hundred meters. You can see layering there, variations in density and composition that tell stories about the object's history. Some layers are clear ice, probably deposited during relatively quiescent periods. Others are clouded with dust and organic material, perhaps from times when the object passed through denser regions of its birth system's protoplanetary disk. But beyond a few hundred meters, the ice becomes opaque to your instruments. You know from models that somewhere down there, kilometers down, the ice transitions to high-pressure phases. Ice 7 forms under the mounting pressure. Deeper still, the temperature rises from gravitational heating, and somewhere, at some depth you can only estimate, there might be liquid water. The thought is dizzying. Standing on this frozen surface, surrounded by ice that reaches -100 degrees, knowing that beneath your feet could be an ocean warmer than the freezing point of water. An ocean that has never seen sunlight. An ocean that exists purely because this object is massive enough for gravity to heat its own interior. If that ocean exists, what does it contain? On Earth, every body of liquid water we've found contains life. Everywhere from boiling hot springs to Antarctic subglacial lakes to the deep ocean trenches. If there's water, there's biology. But this isn't Earth. This water, if it exists, has been isolated for millions of years, possibly longer. If there was biology when the object was ejected from its birth system, could it have survived? Could there be ecosystems down there, adapted to eternal darkness and high pressure, sustained by chemical energy from water-rock interactions? We don't know. Standing here, with kilometers of ice between you and any potential ocean, you have no way to find out. You'd need to drill not hundreds of meters, but dozens of kilometers, through ice that transitions from brittle near-surface material to plastic, flowing ice at depth. Finally, to high-pressure phases with properties unlike any ice on Earth. The equipment for such a drilling program doesn't exist. The power requirements alone would be enormous. And even if you could drill that deep, how would you sample the ocean without contaminating it? How would you ensure that any biology you found was native, not Earth microbes that hitched a ride on your equipment? These are questions without answers. For now, the subsurface ocean, if it exists, remains hypothetical, tantalizingly possible, supported by physics calculations, but unconfirmed. You walk across the surface, careful of the crevasses, heading toward a feature your orbital survey identified, an active zone where recent fracturing has exposed fresher ice from depth. The landscape changes as you approach. The ice here is different, clearer, less weathered by cosmic rays. The surface is rough, jumbled with blocks that have tumbled from the fracture walls. And there ahead you see it, a canyon 5 kilometers deep and 20 kilometers wide, stretching across the landscape as far as you can see in either direction. The canyon walls drop away in step terraces, layers of ice that have fractured and collapsed as sublimation undermines their foundations. You can see the stratigraphy, variations in color and texture that represent different epochs in the object's history. Near the top, the ice is grayish, contaminated with dust and radiation-damaged organics. Deeper, it transitions to clearer ice, blues and whites that catch and refract the sunlight. And at the bottom of the canyon, 4.8 kilometers below you, according to your instruments, there's activity. Even from this distance, you can see jets of vapor erupting from the canyon floor. These aren't the gentle sublimation vents you saw earlier. These are violent eruptions, geysers shooting material hundreds of meters into the air. The plumes catch the sunlight, glowing white against the shadowed depths of the canyon. Your instruments detect water vapor, carbon dioxide, and trace amounts of other compounds. The temperature at the canyon floor is higher than at the surface. Not warm by any means, but perhaps negative 50 degrees Celsius instead of negative 100. The canyon's depth protects it from the cold of space, and solar radiation reflecting off the walls creates a greenhouse effect that warms the floor. But more intriguing, some of those compounds shouldn't be there. Complex organic molecules, more elaborate than anything that should form from simple cosmic ray chemistry. Amino acids, compounds with ring structures, molecules that look suspiciously like they've been processed by something. You can't be sure. The concentrations are low. The compounds might have abiotic explanations, chemistry driven by radiation and heat and pressure over millions of years. But they might not. They might be signatures of processes that require more than simple chemistry. They might be breadcrumbs leading to answers about whether this object carries more than just ice and rock. Before we continue, I want you to consider the strangeness of standing here. You're on an object that originated light years away, in a star system you can't even identify precisely. Everything around you, every atom of ice, every dust grain, every organic molecule, formed in conditions different from our solar system. The isotope ratios are subtly wrong. The chemical abundances don't quite match. Even the ice itself, if you could analyze individual crystals, would tell stories of formation in alien protoplanetary disks. You're standing on a piece of another star system, a sample that traveled for millions of years to reach you, and nobody else in human history has stood where you're standing now. The sun begins to set. Not setting behind a horizon in the usual sense. This world rotates, and as it turns, the sun sinks toward the edge of your local horizon. The light takes on a reddish cast as it passes through more of the thin atmosphere at low angles. Scattered light from dust in the atmosphere creates twilight colors, oranges and reds that seem impossible here. And then the sun dips below the horizon, and everything changes. The temperature drops immediately. Your suit's external sensors show the surface temperature plummeting, negative 120 degrees within minutes, negative 150 within an hour. The sublimation stops. The jets cease. The thin atmosphere begins to freeze, carbon dioxide snowing out first at negative 125 degrees. Then water vapor crystallizing at even lower temperatures. The snowfall is strange, microscopic crystals forming directly in the thin air and settling slowly under the low gravity. They catch the starlight, creating a gentle glitter as they drift down. Upward-facing surfaces accumulate frost rapidly. But it's not like snow on Earth. This is molecular-level redeposition. Gas molecules finding the coldest surfaces and bonding back into solid ice. The wind stops. Without solar heating to drive circulation, the atmosphere becomes perfectly still. The sounds of activity, the hiss of sublimation, the crackle of thermal fracturing all cease. The world goes silent in a way Earth never does. No wind, no water, no biology creating background noise. Just silence so complete it seems to press against your ears. The stars blaze overhead with incredible brilliance. You turn off your helmet lights to appreciate them fully. The Milky Way stretches across the sky, a river of light more spectacular than anything visible from Earth. Individual stars are so clear and sharp they seem three-dimensional, hanging at different depths in the vault of space, and you realize this is what this world has experienced for millions of years. This silence, this darkness, this cold so profound that atoms barely vibrate. The brief warmth of perihelion passage is an anomaly, a few months of activity in a journey measured in eons. But the day-night cycle here is rapid. If this world rotates once every 24 hours, a reasonable assumption given how planets and large bodies typically spin, then night lasts only 12 hours. Before dawn brings the sun back above the horizon, you wait, watching the eastern horizon for the first signs of sunrise. And right on schedule, a glow appears. The sky begins to brighten, not with blue like Earth's atmosphere, but with a pale white glow as the first sunlight hits high-altitude ice crystals in the thin air. And then the sun breaks the horizon, and the transformation begins again, temperature rising, frost sublimating within minutes of being struck by sunlight. Jets reactivating as pressure builds beneath the surface. The thin atmosphere thickening as gas production ramps up. Wind starting to flow from the day side toward the still, cold night side. You're watching a world wake up. Every day it goes through this cycle, freezing solid during night, becoming active during day. Every rotation creates thermal stresses that crack the ice, rework the surface, gradually erode this world into space molecule by molecule. How long can it last? At the current sublimation rate, losing millions of tons per second during daylight at perihelion, the object is shedding a measurable fraction of its mass during each close pass to the sun, maybe 1% total mass lost during this passage. That doesn't sound like much, but it represents trillions of tons of material, enough to noticeably lower the surface level, enough to change the object's mass slightly, if it were to somehow remain in the inner solar system, orbiting the sun. Repeatedly, it would erode away in geologically short timescales, thousands of years, perhaps tens of thousands. But it won't remain. This is a flyby, a single close pass. After perihelion, it will retreat back outward. The sublimation will cease, and the object will return to the frozen dormancy of interstellar space, where it will drift for another million years, perhaps forever, until it either enters another star system or remains wandering the galaxy indefinitely. You take samples, ice cores extracted from various depths, atmospheric collectors capturing the gas mixture, dust traps gathering particles from the sublimation jets. Each sample is a message from another star system, chemistry that formed in conditions we can only infer. Laboratory analysis back on Earth will decode those messages. Isotope ratios, organic complexity, mineral compositions, all telling stories about the alien stellar nursery where this world was born. But some questions can't be answered with the equipment you have. Is there really an ocean beneath you? If so, does it contain anything beyond water and dissolved minerals? Are those complex organics you detected just chemistry, or are they biosignatures? The uncertainty is maddening and exhilarating in equal measure. You're standing on one of the most scientifically valuable objects humans have ever encountered, and you barely have time to scratch its surface before your mission window closes and you must return to orbit. Because this visitor won't wait. It's not in a stable orbit that allows leisurely study. It's passing through on a trajectory that will take it back to the outer solar system within months, then beyond, into interstellar space, where it will fade from view and perhaps never be seen again. You take one last look around, at the ice fields stretching to the curved horizon, at the jets of vapor rising into the black sky, at the sun hanging small and bright above. You try to memorize what it feels like to stand here, knowing that nobody else may ever return to this spot. And then you climb back into the landing craft, seal the hatch, and begin the ascent back to orbit, carrying your samples and your memories and your unanswered questions. But the story isn't over. In the next chapter, we'll pull back to watch. What happens when this massive visitor passes through our solar system, not from the surface, but from Earth, watching the gravitational dance as this interloper perturbs orbits and scatters debris and leaves its mark on our cosmic neighborhood. Because that's when the true scale of this event becomes clear, when you see it not as a world to explore, but as a force of nature, massive enough to reshape the architecture of the solar system itself. The year is 2035. An astronomer in Chile, working the night shift at the Vera C. Rubin Observatory, notices something unusual in the automated detection system. A new object, bright, exceptionally bright, moving against the background stars. The software flags it for review. Standard procedure for anything that moves. But within minutes, the astronomer realizes this isn't standard at all. The trajectory is wrong. Not elliptical, like an asteroid or comet in solar orbit. Not quite parabolic either, like some long-period comets making their first approach from the Oort cloud. This is hyperbolic, an interstellar trajectory. But the orbital energy is different from the handful of interstellar visitors discovered previously. It's moving faster than it should for an object of its apparent brightness. Unless the brightness doesn't come from a small object close by, but from something massive farther away. By dawn, telescopes around the world have turned toward this new visitor. By noon, the preliminary size estimates come in. And by sunset, humanity knows something approximately 12,000 kilometers in diameter is approaching from interstellar space. An Earth-sized comet inbound at 75 kilometers per second. The countdown begins. Closest approach to the Sun, perihelion, will occur in 10 years, 3 months, and 14 days. Humanity has a decade to prepare for something unprecedented. The immediate questions flood in from every scientific institution, every government, every news organization. Where will it pass? Is it dangerous? What will happen? And beneath those practical questions, deeper ones. Why haven't we seen anything like this before? Are such objects common? What does it mean? But here's what we don't know, and what becomes immediately apparent. We've never modeled a scenario quite like this. We have simulations for asteroid impacts, objects a few kilometers across striking Earth at typical solar system velocities. We understand those well enough to calculate energy release, crater size, global effects. We have models for close comet, approaches for gravitational perturbations from passing stellar systems. But an Earth mass object on an interstellar trajectory passing through the inner solar system, That exists in a gap in our preparedness. The first year is devoted to observation and calculation. Every major telescope dedicates time to studying this visitor. Spectroscopy reveals familiar comet chemistry, water ice, carbon monoxide, organics. But the absolute brightness, even at 10 astronomical units out beyond Saturn's orbit, confirms the size estimates. This isn't observational error. This isn't a swarm of smaller objects. It's a single massive world. The gravitational influence calculations begin, and immediately troubling patterns emerge. At its current position, still far beyond Neptune's orbit, the object's gravitational field is already measurable. Kuiper Belt objects in its vicinity show orbital perturbations. Small bodies, the icy remnants from solar system formation, are being deflected, their orbits shifted by the gravitational presence of this interloper. A few trajectories look particularly concerning. Several Kuiper Belt objects have been nudged onto paths that will bring them into the inner solar system decades or centuries from now. Potential impactors sent inward by gravitational billiard ball effects that will play out over generations. There's no immediate danger. The deflected objects won't approach Earth for lifetimes, but the seeds of future meteor storms and potential hazards are being sown in real time. Year 2. The visitor crosses Neptune's orbit. Inbound, the gas giant's orbit shifts, not catastrophically, not enough to disrupt the planet's stability, but measurably. Neptune's orbital velocity changes by several meters per second. Over the coming centuries, Neptune will arrive at different positions in its orbit than it would have without this encounter. The effect will propagate, creating tiny timing differences in planetary alignments that accumulate over millennia. Neptune's largest moon, Triton, experiences more dramatic effects. Already in an unusual retrograde orbit, suggesting it's a captured Kuiper Belt object rather than a moon that formed with Neptune, Triton's orbit decays slightly from the gravitational interaction. Not enough to cause immediate crisis, but enough that over millions of years, Triton's fate might be sealed, eventual collision with Neptune or gravitational disruption into a ring system. But here's what fascinates and terrifies astronomers: the uncertainty in predictions. Gravitational interactions are chaotic. Small changes in initial conditions, tiny uncertainties in the visitor's exact mass, trajectory, or velocity produce large variations in outcomes. Computer models run thousands of times with slightly different parameters produce different results. Most show minor perturbations, some show significant disruptions. A few outlier scenarios predict catastrophic gravitational cascades affecting multiple planets. We don't know which prediction is correct. We won't know until the encounter actually happens and we can measure the outcomes directly. All we can do is watch, calculate, refine our models, and hope the universe chooses one of the gentler scenarios. Year 4. The visitor crosses Uranus's orbit. Uranus, that ice giant tilted on its side with its 98-degree axial tilt, experiences its own gravitational encounter. The planet's axis shifts by a fraction of a degree, not enough to change seasons significantly, but enough to prove the models are working. The visitor's mass and trajectory estimates improve with each planetary encounter. But Uranus's small outer moons aren't so fortunate. These tiny bodies, some barely 10 kilometers across, orbit at the edge of Uranus's gravitational influence. The visitor's gravity, strong at these distances, overwhelms Uranus's weak hold on its outermost satellites. 3 moons are stripped away entirely, sent into independent orbits around the Sun. They join the solar system's population of asteroids and comets, refugees from Uranus, their orbits forever altered by a visitor from another star. By year 6, Earth's population has become acutely aware of the visitor. It's visible now to amateur telescopes, a fuzzy patch of light in the constellation Gemini, growing brighter each month. News coverage intensifies. Doomsayers predict catastrophe. Scientists hold press conferences trying to explain orbital mechanics and gravitational influence zones to a public that mostly hears massive object and approaching Earth and draws their own conclusions. The truth is more nuanced and, in its way, more remarkable than the catastrophe scenarios. The visitor's trajectory will pass within 1.5 astronomical units of the Sun, inside Earth's orbit, but not directly threatening our planet. The timing is fortunate. Earth will be on the opposite side of the Sun during the visitor's closest approach. No collision risk, no gravitational capture into a bound orbit. Just a flyby, dramatic but not deadly. Still, effects are inevitable. Earth's orbit will shift slightly. Perhaps a few kilometers difference in orbital radius, perhaps a tiny change in orbital velocity. The seasons might shift by a day or two over the coming centuries as accumulated perturbations affect Earth's position in its orbit. The Moon's orbit around Earth might wobble fractionally. Nothing catastrophic, but permanent fingerprints left by this encounter. Year 7, Saturn's turn. And this is where things become visually spectacular from Earth. Saturn's ring system, those iconic bands of ice and rock, responds to the visitor's gravitational pull. The rings are thin, fragile structures held in place by a delicate balance of orbital mechanics and gravitational resonances with Saturn's moons. The visitor disrupts that balance. Density waves propagate through the rings, ripples moving outward from disturbance points, creating temporary patterns that make the rings appear to shimmer and pulse. Some ring particles are accelerated into slightly different orbits. A few, a tiny fraction, but millions of individual particles, are pulled entirely free of Saturn, becoming microscopic comets that will drift through the solar system until they eventually collide with something or get swept up by a planet's gravity. From Earth, equipped with powerful telescopes, astronomers watch the rings transform. The changes are subtle, not the kind of thing visible to the naked eye, but under close observation. The ring structure shows perturbations that will persist for decades before the system settles back into equilibrium. Saturn itself, massive enough to mostly shrug off the encounter, still feels effects. Its orbital velocity changes by meters per second. Its position in orbit will be slightly different centuries from now because of this brief gravitational interaction. And its inner moons, those shepherd moons that help maintain the rings, experience orbital changes that will take years for the system to accommodate. By year 8, the visitor dominates the night sky from Earth. It's approaching Jupiter's orbit now, and its activity has ramped up dramatically. Solar heating at this distance is intense enough to drive vigorous sublimation. The coma, that cloud of gas surrounding the nucleus, has grown to several million kilometers in diameter. The tail stretches behind it, growing longer each week as material sublimates from the massive surface and gets pushed away by solar wind. From Earth, the tail appears as a glowing bridge across the sky. Not quite as bright as the full moon, but bright enough to be unmistakable. Bright enough to cast faint shadows on moonless nights. Bright enough that city lights can't wash it out entirely. People around the world look up and see this cosmic visitor, this messenger from another star, making its closest approach in human history. But here's what most people don't realize: they're watching. That tail represents the visitor literally evaporating into space. At the current sublimation rate, millions of tons per second, the object is losing a measurable fraction of its mass. Perhaps 1% total over the course of this perihelion passage. Trillions of tons of material, ancient ice from another star system, now dispersed across the inner solar system. Some of it will eventually drift into interstellar space. Some will be captured by planets. Thin streamers of gas and dust that will rain down on atmospheres or accrete onto airless bodies. And some will settle into orbits that intersect Earth's path. For years after this encounter, Earth will experience meteor showers as our planet passes through debris streams from the visitor. The meteors will be unusual, richer in water and organics than typical solar system meteors, carrying chemistry from an alien star system. Every shooting star during those showers will be a tiny piece of the visitor, burning up in Earth's atmosphere after traveling light years to get here. Year 9. Jupiter. And this is the encounter everyone has been waiting for, with a mixture of anticipation and dread. Jupiter is massive, 318 Earth masses, the dominant gravitational force in the solar system after the Sun itself. The visitor, at perhaps 1/3 Earth's mass, is tiny by comparison, but it's still massive enough that the interaction is mutual. Both objects will affect each other. The visitor approaches within 1 astronomical unit of Jupiter, not a close pass by astronomical standards, but close enough for significant gravitational interaction. The encounter functions as a gravitational slingshot in reverse. Jupiter's immense gravity bends the visitor's trajectory, slowing it slightly and redirecting it more sharply toward the inner solar system. Jupiter, in exchange, feels the pull. Its orbital velocity increases by several hundred meters per second. Not much for such a massive planet, but real. Jupiter's orbit expands outward by a few kilometers. Over millennia, this tiny change will propagate through the solar system's gravitational architecture, affecting the orbital positions of all the planets in subtle ways. Jupiter's moon system experiences more dramatic effects. The Galilean moons, Io, Europa, Ganymede, Callisto, all feel gravitational tugs from the passing visitor. Their orbits shift slightly. Europa, that ice-covered moon with its subsurface ocean, experiences enhanced tidal flexing during the encounter. The additional tidal stress might trigger increased geological activity. More cracks in the ice, more geysers, more heat generated in the interior. But it's the outer irregular moons, those small captured objects orbiting far from Jupiter, that experience the most change. Several are stripped away entirely, their weak gravitational connection to Jupiter overwhelmed by the visitor's pull. They become independent objects orbiting the Sun, refugees from Jupiter's system, their futures uncertain. And then, trajectory bent by Jupiter's gravity, the visitor accelerates inward toward perihelion. Year 10. The culmination. The passage through the inner solar system. By now, every space telescope, every ground-based observatory, every amateur astronomer with a backyard setup is watching. This is the event of the century, perhaps the event of human history up to this point. An Earth-sized world from another star, passing within 1.5 astronomical units of the Sun, close enough that its activity reaches a crescendo. The sublimation rate becomes phenomenal. Entire hemispheres of surface ice evaporate in real time. The coma expands to dimensions larger than the Sun. The tail stretches beyond Mars's orbit, a glowing structure more than 100 million kilometers long, visible from Earth as an arc that spans 40 degrees of sky. The temporary atmosphere thickens to Mars-like pressures in places, sustained by the ferocious outgassing. Cloud systems form, carbon dioxide clouds on the night side, water ice crystal clouds in the upper atmosphere. Lightning flashes in the sublimation plumes, triggered by static electricity from colliding ice particles. This isn't a comet as we've ever seen comets. It's a world in crisis, shedding its substance into space at rates that would erode a normal comet completely in weeks. The surface changes visibly day by day. Ice cliffs hundreds of meters high collapse as their foundations sublimate away. Crevasses widen. New fractures open across entire hemispheres as thermal stress overwhelms structural strength. If there are subsurface ocean regions, the reduced overburden from surface loss might allow them to erupt cryovolcanoes, shooting liquid water into space where it instantly freezes into ice particles that rain down across thousands of kilometers from Earth. The spectacle is breathtaking and humbling. The tail dominates the sky for weeks around perihelion. During the closest approach, the nucleus itself is visible as a disk rather than a point. The only comet in history large enough to show a resolved shape from Earth's distance. Spectroscopic analysis reveals the chemical composition in unprecedented detail, isotope ratios, organic molecular complexity, mineral signatures, all broadcasting information about the alien star system where this world formed. And then, as quickly as it approached, it passes. Perihelion lasts only days at the visitor's velocity. The closest approach to the sun comes and goes. The object races past, bent by solar gravity but not captured, its interstellar velocity still sufficient to escape. Now it's headed back outward, away from the sun, back toward the outer solar system, and eventually to interstellar space. The sublimation begins to slow as solar heating decreases. The tail gradually shrinks. The temporary atmosphere freezes and snows back to the surface. The jets stop. The cryovolcanoes, if they existed, seal themselves as pressure equalizes. The world that was briefly awake returns to dormancy. Year 12, crossing Jupiter's orbit again on the way out. Another gravitational interaction, but weaker this time due to different geometry and lower relative velocity. Jupiter steals some orbital energy, slowing the visitor fractionally, but not enough to trap it. The visitor continues outward. Year 15, Saturn, Uranus, Neptune again. Each encounter leaves subtle gravitational fingerprints on both the planets and the visitor. Orbits shift by tiny amounts. Timing changes accumulate. The solar system's architecture has been permanently altered, if only slightly. Year 20, the visitor crosses the heliopause, that boundary where solar wind gives way to the interstellar medium. It's leaving. The solar system's gravitational hold fades. Ahead lies the great dark between stars, the realm the visitor briefly left and now returns to. But it's changed. Smaller now, perhaps 5 to 10% less massive from the material sublimated away during perihelion passage. The surface has been reworked, fresh ice exposed, older layers stripped away. Whatever internal structure it had before has been modified by the thermal stress of solar heating, and it carries something new, solar system material. During its passage, it swept up microscopic dust grains, captured molecules from planetary atmospheres, possibly even picked up micrometeorites from the asteroid belt. When it enters its next star system, if it ever does, it will bring samples of our solar system with it. Chemistry from our sun, perhaps even organic molecules from Earth, if any made it high enough into our atmosphere to be swept up. The reciprocity is beautiful. We received a sample from another star system, and in exchange, we sent some of our own chemistry back into the galaxy. But here's what we don't know, and what will haunt astronomers for generations. What permanent changes did this encounter create? The orbital perturbations are calculable in principle, but chaos theory limits prediction accuracy. Small changes now might amplify over millions of years into significant effects. Could the visitor's gravitational tugs have set up resonances that will eventually destabilize orbits? Could asteroids deflected during this passage become impactors centuries from now? Could the moon's orbital wobble accumulate into measurable changes in Earth's tides over millennia? We don't know. We can model, we can simulate, but the solar system is a chaotic system where small perturbations compound unpredictably. The true legacy of this encounter might not be known for thousands of years, and there's a deeper mystery. How common are such encounters? This was the first Earth-sized interstellar visitor ever detected. Does that mean they're rare? Or does it mean we only recently developed the technology to spot them? Are there more out there? Dozens, hundreds, thousands, passing through the galaxy undetected because they move through regions where no telescopes watch? The statistics are uncertain. 3 interstellar objects detected in 7 years before this one suggests a certain population density. But all 3 were much smaller. Scaling laws suggest that if Earth-sized objects follow the same size distribution as smaller objects, they should be extremely rare, perhaps only one passing through the inner solar system every few thousand years. But we don't know if that scaling law holds. Maybe Earth-sized objects are ejected from planetary systems at different rates than smaller comets. Maybe they're more stable during interstellar transit, surviving where smaller objects would be destroyed by tidal forces from passing stars. Maybe they're actually more common than predicted, and we've just been lucky or unlucky to encounter one so soon. The visitor fades from view. Within a few years of crossing Neptune's orbit outbound, it's too distant and too dark to detect with current telescopes. It becomes a memory, a data set, a subject for papers and dissertations and endless analysis. But the solar system remembers. The orbital shifts remain. The deflected asteroids continue their new paths. Earth passes through the debris streams each year, creating meteor showers that will persist for centuries. And somewhere in archives and museums, samples collected during those meteor showers wait, tiny fragments of ice and dust from another star system, preserved for future generations to study with techniques we haven't invented yet. The encounter becomes part of human history. The year an Earth-sized world from another star passed through our cosmic neighborhood. The year we watched something impossible happen. The year we realized viscerally that the galaxy is not empty, that star systems are not isolated, that we live in a universe where worlds wander between suns and occasionally, rarely, pass close enough for us to witness. In the next chapter, we'll explore what this encounter taught us, not just about this specific visitor, but about the broader implications for understanding the galaxy, the transport of material between star systems, and the profound question of whether life itself might travel on these cosmic arcs, because that's where the visitor's legacy becomes truly significant. Not in the orbits it perturbed or the spectacle it created, but in what it revealed about connections we didn't know existed. October 19th, 2017. A telescope in Hawaii, part of the Pan-STARRS survey system, captures an image of a field of stars. The software compares it to images taken days earlier and flags something moving. The object is faint, already leaving the solar system by the time it's detected. Within weeks, every major telescope capable of reaching it is scrambling for observations, because the trajectory calculations reveal something that shouldn't be possible. This object isn't orbiting the sun. It's leaving at 87,000 kilometers per hour, following a hyperbolic path that means it came from interstellar space and will return there. They name it Oumuamua, a Hawaiian word meaning scout or messenger from afar. The first confirmed interstellar visitor in human history. But here's what made Oumuamua more than just a curiosity. It was weird. The shape appeared highly elongated, perhaps 10 times longer than it was wide, tumbling end over end as it raced away. Nothing in our solar system looks quite like that. And as astronomers tracked it, they noticed something strange. It was accelerating. Not much, but measurably. Something was pushing it faster than gravity alone could explain. Comets accelerate when they outgas. Jets of sublimating ice create tiny thrust. But Oumuamua showed no coma, no tail, no evidence of the gas and dust that characterizes comet activity. So what was pushing it? The hypotheses multiplied. Maybe it was outgassing something we couldn't detect. Hydrogen, perhaps, which wouldn't show up in the wavelengths we were observing. Maybe it had an unusually reflective surface that solar radiation pressure could push. Maybe it was composed of strange ices that sublimate without creating visible comas, or, and this is where things got genuinely controversial, maybe it wasn't natural at all. Several prominent astronomers, including Harvard's Avi Loeb, suggested seriously that Oumuamua's properties matched what you'd expect from a light sail, an artificial structure designed to be pushed by starlight. The elongated shape, the non-gravitational acceleration, the lack of comet-like outgassing, all consistent with technology rather than nature. The suggestions sparked fierce debate. Most astronomers argued for natural explanations, even if those explanations required unusual circumstances. But the debate revealed something important. We don't actually know what the full range of natural interstellar objects looks like. We've seen so few that outliers, objects with unusual properties, might actually be normal for the broader population. Oumuamua disappeared from view before we could resolve the mystery. It's now beyond Neptune's orbit, headed back into interstellar space, carrying its secrets with it. We'll never know for certain what it was. 2 years later, in August 2019, another interstellar visitor appeared, 2I Borisov. And this one was clearly a comet. It showed a bright coma. It had a classic tail. Spectroscopy revealed gas composition, carbon monoxide and water vapor in ratios that could be measured precisely. 2I Borisov behaved exactly as a comet should behave, following all the patterns we expect from our solar system's comets, except the chemistry was wrong. Subtly wrong, but measurably different. The ratio of carbon monoxide to water was higher than in solar system comets. Not wildly different, we're talking about variations of perhaps 50%, but real. That difference tells a story about formation conditions in 2I Borisov's birth system. Higher carbon monoxide ratios suggest formation in a colder region, or in a protoplanetary disk with different chemistry than the one that formed our sun and planets. Here was direct chemical sampling of another star system's planet-forming region. No need to travel light years, no need to wait centuries for interstellar probes. The sample came to us, carrying messages written in isotope ratios and molecular abundances, and now 3I Atlas in 2024. Another comet, another interstellar trajectory, another set of chemical signatures that are almost, but not quite, solar system normal. 3 confirmed visitors in 7 years. But here's what we don't know. How many did we miss? These objects are faint. They move fast. They spend limited time in the inner solar system where detection is easiest. Before Pan-STARRS and other modern survey systems began operating, we simply weren't looking in the right way to spot them. How many interstellar visitors passed through during the 20th century, unseen because no one was watching? How many pass through the outer solar system right now, too distant and dark to detect with current technology? The statistics are maddeningly uncertain. Based on 3 detections in 7 years, researchers estimate that perhaps one interstellar object larger than a few hundred meters passes within Earth's orbit annually. Scale that up to the entire solar system, and you get perhaps 5 to 10 objects per year entering from interstellar space. But those numbers have huge error bars. Maybe the rate is half that. Maybe it's double. We don't have enough data to know. And the size distribution, the relationship between how common small objects are versus large ones, remains almost completely unknown. Do Earth-sized interstellar objects exist? If so, how often do they pass through star systems? Once per million years? Once per billion? Or are they common enough that one might appear in the coming centuries? We don't know. What we're learning, though, is that interstellar space is not empty. It's populated with refugees from planetary system formation, objects ejected during the chaotic early epochs when planets were still forming and gravitational interactions were violent, and common current models suggest that most young planetary systems eject more mass than they retain. For every kilogram of material that ends up in planets, several kilograms get flung into interstellar space. Multiply that by hundreds of billions of star systems forming over billions of years, and you get a staggering number. Trillions of objects wandering the galaxy at any given moment. Most are small, pebbles, boulders, mountain-sized chunks. But the size distribution might extend upward. If small objects get ejected readily, why not large ones? During close encounters between forming planets, even massive bodies can be accelerated to escape velocity. Some simulations suggest that rogue planets, world-sized objects unbound from any star, might outnumber planets in stable orbits. If that's true, the galaxy's true planetary census is invisible. For every planet we can see orbiting a star, there might be several wandering the darkness between stars, orphaned during their birth system's turbulent youth, and some of those orphans might be massive enough to retain internal heat. Not from sunlight, there is no sun, but from radioactive decay of elements in their cores, or from residual heat from formation, or from tidal friction if they have large moons. Enough heat to maintain subsurface oceans beneath protective ice crusts, worlds in eternal darkness, possibly harboring ecosystems that evolved independent of any star. Life, if it exists there, would be utterly alien, adapted to high-pressure, total darkness and chemical energy sources rather than photosynthesis. But physics allows it. Biology, based on Earth's extremophiles, suggests it's possible. We have no way to detect such objects with current technology. They emit no light. They're too small to cause measurable gravitational lensing, except in vanishingly rare alignments. They're invisible wanderers, potentially more numerous than stars themselves, but hidden in the darkness. Before we continue, consider what this means for our understanding of life in the galaxy. We've spent decades searching for biosignatures on exoplanets, looking for oxygen in atmospheres, methane in unexpected abundances, chemical combinations that suggest biological processes. That search assumes life requires a planet orbiting a star. But if rogue worlds are common, and if some harbor subsurface oceans, then biospheres might exist in places we're not looking. More intriguingly, interstellar objects might be the mechanism by which life spreads. The hypothesis is called panspermia, the idea that life doesn't originate independently in each star system, but spreads between systems on natural carriers. It's been speculative for over a century, proposed by scientists including Francis Crick and Fred Hoyle, but always lacking a plausible mechanism. Interstellar objects provide that mechanism. Imagine a planet with active biology, oceans teeming with microbial life, possibly more complex organisms. During the chaotic planet formation epoch, or later during close encounters with other massive bodies, material gets ejected from the planet. Some of that material might include water, from oceans, from ice, from atmospheric escape. And in that water, frozen instantly by the cold of space, could be microbes. The microbes enter suspended animation. At near absolute zero temperatures, molecular motion effectively stops. No metabolism, no growth, no decay, just stasis. Preserved as perfectly as anything frozen in permafrost or ancient ice, the ice, carried on comets or larger bodies, travels between star systems. The journey takes millions of years. But if the microbes are truly dormant, if their cellular machinery is preserved without degradation, they might survive. Eventually, statistically inevitable given enough time, the object enters a new star system. Solar heating warms it. Ice begins to melt, first on the surface, eventually potentially in subsurface oceans if the object is massive enough. And the microbes wake up. If they find themselves in liquid water with available chemistry, they might resume metabolism, grow, reproduce, seed the new star system with life from the old. It sounds like science fiction. But here's what we know. Life on Earth survives incredible extremes. We've found bacteria in million-year-old ice cores from Antarctica. We've revived microbes frozen in permafrost for hundreds of thousands of years. We've tested organisms in space, exposed to vacuum, radiation, temperature extremes, and many survive. The mechanisms exist. Proteins that prevent ice crystal damage, DNA repair systems that fix radiation damage, cellular states so dormant that they're barely distinguishable from death. The question isn't whether individual microbes could survive interstellar transport. The question is whether enough survive in sufficient numbers and diversity to establish ecosystems on the other end. We don't know. We have no examples of successful panspermia. Life on Earth might have originated here independently, or it might have been seeded from elsewhere. We can't tell from the evidence we have. Mars sample return missions might provide clues if Martian life exists and shares biochemistry with Earth. That would suggest common origin, possibly via meteorite transport between planets. But interstellar panspermia remains unproven. Plausible, supported by physics and biology we understand, but unconfirmed. our hypothetical Earth-sized comet makes the scenario more plausible. A massive object with subsurface liquid water protected from radiation by kilometers of ice provides an ideal transport mechanism. Entire ecosystems could potentially survive the journey, not just individual microbes. The internal ocean, if it exists, would be a self-contained biosphere, isolated from the harsh exterior, maintaining stable conditions even during million-year transits. But here's what troubles the hypothesis: the statistics. Even if interstellar objects are common, even if some are massive enough to harbor subsurface oceans, even if those oceans occasionally contain life, the probability of successful seeding is vanishingly small. Most objects never enter star systems. They drift through interstellar space indefinitely. Of those that do enter systems, most don't approach close enough to planets for material exchange. And even if they pass close to a planet, the mechanism for life transfer is unclear. Does the object crash? Does it release material that the planet captures gravitationally? How do microbes get from the object's interior to the planet's surface in viable condition? Each step has low probability. Multiply those probabilities together, and successful panspermia events become rare even on galactic timescales. Unless the galaxy is older than we typically consider, and rare events have had billions of years to occur repeatedly. The Milky Way has been forming stars for over 13 billion years. Early stellar generations were mostly massive stars that lived fast and died young. But within a few billion years, sun-like stars with potential planetary systems became common. That's 10 billion years of planetary formation, 10 billion years of interstellar object ejection, 10 billion years for rare events to accumulate. If panspermia happens once per galaxy per billion years, that's still 10 seeding events in our galaxy's history. If each successful seeding leads to a biosphere that eventually produces its own ejected material, you get a cascade, life spreading from system to system over deep time, creating a network of related biospheres connected by interstellar travelers. We don't know if this happens, but the detection of interstellar objects, the realization that material exchange between star systems is common, makes it seem less like speculation and more like a testable hypothesis. The test requires missions. We need to intercept interstellar objects and sample them directly. Surface composition is a start, but the real information is in the interior, the protected regions where complex chemistry or even preserved biology might survive. Several mission concepts exist. Project Lyra, designed by the Initiative for Interstellar Studies, calculated trajectories to catch Oumuamua using heavy-lift rockets and solar Oberth maneuvers, diving close to the Sun to gain velocity through gravitational assists. The conclusion: technically possible with current technology, but requiring enormous fuel loads and precise timing. Future missions might target newly detected interstellar visitors with more lead time. The challenge is the detection-to-intercept window. These objects are typically discovered when they're already inbound, leaving limited time for mission planning, construction, and launch. What we need is earlier detection, spotting objects years before they reach the inner solar system, providing time to prepare. The Vera C. Rubin Observatory, now fully operational, changes that equation. Scanning the entire visible sky every few nights, it will detect interstellar visitors much earlier, potentially when they're still beyond Jupiter's orbit. That provides years of warning, enough time to design and launch intercept missions. What would such missions find? The chemistry is almost certain to be fascinating. Isotope ratios from alien star systems, organic complexity created during interstellar transit, minerals and ices that reveal formation conditions light years away. Each sample is a message from another stellar neighborhood, chemistry that formed under different conditions than anything in our solar system. But the possibility that keeps astrobiologists awake at night: what if we find biosignatures? Not life itself. Nothing could metabolize in the frozen interior. but signs that life was once present: amino acids with chirality bias, lipid membranes preserved in ice, maybe even fossilized cellular structures if we're incredibly lucky. Evidence that the object originated in a star system with active biology, carrying frozen samples of alien biochemistry. That discovery would transform our understanding of life's place in the universe. It would prove that biospheres are not isolated, that chemistry and possibly biology spreads between stars, and that the galaxy is more connected than we imagined. But it would also raise profound questions. If life spreads between systems, where did it originate? Is there a single origin point, one early biosphere that seeded the galaxy, or multiple independent origins that have since mixed? Could Earth's life be the descendants of microbes from another star, making us all aliens, in a sense? We don't know. The data doesn't exist yet. But within our lifetimes, within decades perhaps, we might have answers, because the visitors keep coming. 3 confirmed in 7 years, dozens expected in the coming decade as detection systems improve. Hundreds within our lifetimes, if current projections hold. Each one an opportunity. Each one a sample from elsewhere in the galaxy. Each one potentially carrying messages about chemistry, planet formation, and maybe even life itself. The real revolution isn't finding an Earth-sized visitor, though that would be spectacular. The real revolution is the realization that the galaxy is not empty space between isolated islands. It's a web with material constantly flowing between the nodes. Chemistry spreads. Organic molecules travel, and possibly, just possibly, life itself journeys between the stars on natural rafts of ice and rock. Our thought experiment about an Earth-sized comet connects to this deeper truth. By exploring what such an object would be like, its internal oceans, its potential for harboring ecosystems, its effects on our solar system, we're preparing ourselves for possibilities that might seem wild, but are grounded in physics we understand. In the final chapter, we'll look forward to what's coming. The next generation of telescopes and detection systems, the missions being planned, the discoveries that wait in the data we'll collect over the coming decades, and what it all means for humanity's place in a galaxy that's turning out to be far more dynamic, connected, and potentially alive than we once imagined, because this is just the beginning. The first chapter in a story that will unfold over centuries. The moment when humanity realized that we're not observing a static universe, but one in constant motion, where worlds wander and chemistry spreads, and connections exist that we're only beginning to trace. The telescope sits atop Cerro Pachón in Chile, 8,000 feet above sea level, where the air is thin and the skies are among the darkest on Earth. The Vera C. Rubin Observatory, with its 8.4-meter mirror and 3 billion pixel camera, began full operations in 2025. And it's changing everything. Every 3 nights it images the entire visible sky. Every image is compared to previous ones by software that flags anything that moved: asteroids, comets, satellites, and interstellar objects. Before Rubin, we found interstellar visitors by accident, astronomers spotting unusual trajectories while looking for something else. Oumuamua was already leaving when we detected it. Douai Borisov gave us a few months of observation time. 3I Atlas, discovered by Atlas telescopes, provided perhaps half a year of quality data before it faded from view. But Rubin changes the game. It's designed to catch objects early, when they're still far out, still approaching. Early projections suggested it might find 1 interstellar visitor per year. Recent refinements of the statistics, based on the discovery rate from 2017 to 2025, suggest something more dramatic: 5 to 10 per year, maybe more. By 2030, astronomers expect a catalogue of dozens of interstellar objects with well-characterized orbits, trajectories traced back to their origins, compositions measured through spectroscopy, sizes estimated from brightness and thermal emission. By 2040, hundreds. And here's what we don't know yet, but will soon discover: the size distribution. Are small objects common and large ones rare, following a power law like asteroids do? If so, Earth-sized interstellar objects might pass through the inner solar system once per million years, rare enough that observing one would be extraordinary luck or extraordinary timing. Or is there a preferred size from formation physics? Maybe objects in a certain mass range, large enough to survive tidal disruption during ejection, small enough to actually be ejected rather than retained, dominate the population. That could mean more large objects than simple scaling predicts. Or, and this is the possibility that fascinates me, maybe the size distribution extends further than we imagine. Maybe planet-sized rogues are common enough that one passes through every few thousand years. Maybe we're living in the brief window when humanity first develops the technology to detect them, and one happens to appear. We won't know until we have the data. Another 5 years of Rubin observations should tell us. 10 years will give us statistical confidence. 20 years will reveal patterns we can't currently guess. But the statistics are just the beginning. The real discoveries will come from what those objects are made of. Each interstellar visitor is a sample from another star's planetary formation region. The chemistry, isotope ratios, molecular abundances, mineral compositions, records conditions in that distant protoplanetary disk. By studying enough visitors from enough different origin points, we can map chemical diversity across the galaxy. Our star systems in the galactic center, where metallicity is higher, producing different ice chemistries than systems in the outer spiral arms. Do younger star systems eject material with compositions distinct from older ones? Can we trace back specific visitors to specific stellar populations and learn about planet formation conditions without ever traveling to those stars? These questions will be answered through spectroscopy and eventually sample return. But there's a deeper mystery that spectroscopy alone can't resolve. What's inside? Remote sensing tells us surface composition. Light reflected and absorbed by the outer layers. Gas sublimating from the top few meters. But the interior, the bulk of the material, the protected regions where cosmic ray processing hasn't penetrated, remains hidden. That's where the most interesting chemistry might be. Complex organics created during interstellar transit. Minerals that formed during the object's birth and were never altered by subsequent heating. Ice that preserves the exact composition of the original protoplanetary disk. And possibly, however unlikely, preserved biological material if the object originated in a system with active biospheres. We need to go there, to intercept these visitors and sample them directly. The mission concepts exist. Engineers have designed trajectories. The physics is understood. What's missing is the combination of early detection and rapid response that makes intercept practical. Here's the challenge. Interstellar objects move fast. They're not in solar orbit, so you can't plan a rendezvous years in advance like you can with asteroids or comets. By the time we detect them, they're typically already inbound, giving maybe months of warning before they pass perihelion and start their outbound journey. Matching velocity with an object moving at 70 or 80 kilometers per second requires enormous energy. Chemical rockets alone can't do it unless you're willing to launch fuel loads that dwarf the payload. You need gravity assists, using planets as gravitational slingshots to build up speed, or exotic propulsion like solar sails that accelerate continuously, or nuclear engines that provide thrust for months. Project Lyra, a study by the Initiative for Interstellar Studies, calculated one approach: launch toward the Sun. Dive extremely close, within a few solar radii, using solar heat shields developed for other missions. At closest approach, fire engines to gain velocity. The combination of gravitational slingshot and propulsive kick can potentially reach the velocities needed to chase down interstellar visitors. The maneuver is dangerous. Solar radiation at that distance can fry electronics and ablate heat shields. Timing must be perfect. But it's possible with near-term technology. Alternative approaches use multiple gravity assists from inner planets, Earth, Venus, Mercury, building up speed through a carefully choreographed dance of close flybys. Or they accept that matching velocity is impossible, and instead design impactor missions, fast probes that collide with the interstellar object at high relative velocity, sending debris into space where follow-up spacecraft analyze the ejecta. But all of these approaches require early detection. If Rubin or future surveys can spot interstellar visitors when they're beyond Jupiter's orbit, 5 astronomical units out, giving 5 to 10 years before perihelion, then we have time to design, build, and launch missions. Time to calculate optimal trajectories. Time to coordinate multiple spacecraft for different aspects of the encounter. And if we detect an Earth-sized visitor approaching, priorities shift immediately. An object that massive, potentially harboring subsurface oceans, becomes the highest priority target in astrobiology. Everything we've discussed, the internal structure, the liquid water layer, the possibility of preserved ecosystems, transforms from theoretical speculation to urgent investigation. Imagine the mission profile. Detection occurs early, 10 astronomical units out, 10 years before perihelion. The international space community mobilizes. Multiple missions launch over the following years. First, a fast flyby probe launched within the first year, designed to arrive well before perihelion and capture initial imagery and spectroscopy. It characterizes the surface, measures the thermal emission to constrain internal structure, maps sublimation patterns as solar heating begins. Second, an orbiter launched 2 years later with enough fuel to enter orbit around the visitor near perihelion. It conducts extended observations, high-resolution mapping, gravity field measurements to determine mass distribution and detect the liquid ocean layer, if present. Continuous monitoring of sublimation rates and atmospheric dynamics. Third, a lander-driller combination launched 3 years in, time to arrive during the peak activity period. It touches down in a selected location, perhaps near an active fracture zone, where deeper material is exposed, and drills as far as technology allows. Tens of meters ideally, possibly hundreds, if advanced drilling technology is developed specifically for this mission. Samples are analyzed in situ and, if possible, returned to the orbiter for later return to Earth. Fourth, an impactor analyzer pair launched 4 years in. The impactor strikes a specific target, maybe a fresh crater, maybe an active geyser source, excavating material from depth. The analyzer flies through the debris plume, capturing particles and analyzing them in real time with mass spectrometers, organic chemistry instruments, and microscopes looking for cellular structures. The data from these missions would be unprecedented. Direct sampling of another star system's planet-forming material, measurements of internal ocean properties if it exists, searches for biosignatures or preserved biology, chemical analysis revealing the full complexity of organics that formed during interstellar transit. What would we find? The answer genuinely depends on the object's history. If it was ejected recently, within the last 10 million years, from a system with active biology, organic biosignatures might survive. Amino acids showing chirality bias, the left-handed versus right-handed molecular asymmetry that characterizes biology on Earth. Lipid molecules that suggest membrane formation. Maybe even preserved microbes if freezing happened quickly enough to prevent ice crystal damage. But if the ejection happened billions of years ago, biological material would likely be degraded beyond recognition. Cosmic rays break down complex molecules over millions of years. Even frozen, protected material accumulates radiation damage. We might find hints. Organic complexity beyond what abiotic chemistry typically produces, but not definitive proof. And here's the uncertainty that will drive debate for decades. How do you prove something is biological rather than just complex chemistry? On Earth we have context. We can examine cellular structures, genetic material, metabolic processes. But with a frozen sample from an alien biosphere, if that's what we find, those tools might not apply. If alien biochemistry uses different molecules than Earth life, we might not recognize it. If cells have different structures, we might miss them. If genetic information is stored in molecules other than DNA and RNA, our instruments might not detect it. The search for alien biosignatures is fundamentally harder than people imagine. We're looking for patterns, chemical signatures, structural complexity, isotope fractionations that suggest biological processing. But nature can be deceptive. Abiotic processes can create surprising complexity. We've found amino acids in meteorites that definitely didn't come from biology. We've synthesized organic molecules in laboratories using only simple chemistry and energy sources. The only definitive proof would be finding something actively alive and metabolizing. But on a frozen interstellar object, nothing metabolizes. Everything is dormant or dead. We're looking at remnants, traces, chemical fossils. And interpreting those traces is where the uncertainty lies. Still, even negative results would be scientifically valuable. If we study dozens of interstellar objects over the coming decades and find no biosignatures, no preserved biology, no hints of life's chemistry, that tells us something important. Either life is rare, or it doesn't travel well on interstellar objects, or panspermia is not a significant mechanism for life's spread. That would support the hypothesis that biospheres evolve independently, that life on Earth, if we find it, originated here or elsewhere in our solar system without input from distant stars. It would suggest the galaxy contains isolated pockets of biology, each with unique origin stories, each potentially using different biochemistry. But if we do find biosignatures, if even one interstellar visitor shows clear evidence of complex organics organized in ways that suggest biological processing, that changes everything. It would prove that chemistry and possibly biology spreads between star systems. It would suggest that the galaxy is more interconnected than we imagined, with life potentially seeding from system to system over deep time. It would mean that Earth's biosphere might be descended from microbes that arrived here billions of years ago on interstellar debris, making us all children of alien stars in a very real sense, and it would raise the profound question, where did life originate? If panspermia is real, if life spreads between systems, then somewhere there's an origin point, the first biosphere. The place where chemistry first became biology and then spread outward through ejected material. Is it still active? Did it arise in the early galaxy 10 billion years ago, giving life eons to spread? Or are there multiple origin points, independent genesis events that have since mixed their chemical signatures? We don't know. We can't know from the data we have. But future discoveries might provide clues, patterns in the chemistry of interstellar visitors suggesting common origins, or diversity, suggesting multiple independent sources. The philosophical implications are staggering. If life spreads through the galaxy naturally, then the universe might be far more alive than our current observations suggest. Those rogue planets drifting in darkness? Some might harbor ecosystems. Those distant star systems we study through telescopes? They might be connected to ours through ancient exchanges of material and chemistry, and possibly biology itself. We're not isolated. We're part of a galactic ecosystem that operates on timescales of millions and billions of years, where matter cycles between stars, where chemistry becomes increasingly complex through iteration, where life, if it exists widely, might be a galactic phenomenon rather than isolated pockets. But these are the questions we'll spend the next century answering. The data is coming. The missions are being planned. The technology is developing. Within our lifetimes, we'll have answers to questions that have been speculative for as long as humans have wondered about the stars. The coming decades will bring discoveries we can barely imagine. With dozens of interstellar visitors detected annually, we'll map their origins across the galaxy. We'll identify which stellar populations produce which chemistries, We'll potentially trace individual objects back to specific star-forming regions, or even specific star systems. We'll detect outliers, objects with compositions that don't match anything we've seen before, hinting at formation conditions outside our current models. We'll find diversity we didn't expect, rocky interstellar asteroids alongside icy comets, objects with exotic mineral compositions, maybe even visitors with properties that challenge our understanding of what's naturally possible. And somewhere in that data, we might find the big one, the Earth-sized visitor, the massive wanderer that makes our thought experiment real. It might not happen in the next decade. Statistically, such objects are probably rare, but rare doesn't mean never. And with improved detection systems watching the sky continuously, even rare events become detectable given enough time. When it happens, if it happens, humanity will witness something unprecedented, not just scientifically fascinating, but civilizationally significant. The passage of a world through our solar system, close enough to study, massive enough to matter gravitationally, carrying messages from another star written in ice and chemistry, and possibly biology itself. The encounter would galvanize global cooperation. Nations would pool resources for the mission launches. The data would be shared internationally, too important to keep secret, too valuable to restrict. Humanity would come together briefly, united by curiosity about this visitor from the void. And after it passes, after it returns to interstellar space, carrying with it some small amount of solar system material, dust captured during passage, molecules from planetary atmospheres, chemistry from our sun mixed with its own, will be left with the data. Years of observations to analyze, samples to study in laboratories, questions to debate in conferences and papers. But more than data, we'll be left with a changed perspective, the realization, visceral and undeniable, that the universe is not static, that star systems are not isolated, that we live in a galaxy in constant motion, where worlds wander and chemistry spreads and connections exist that we're only beginning to trace. Our thought experiment, scaling 3I Atlas to Earth size, started as a way to explore extreme physics. What happens when you make a comet as massive as a planet? How does gravity reshape it? What internal structures form? What would it be like as a place? But the real value of the thought experiment is this: it prepares us. It builds the conceptual framework for understanding objects we haven't observed yet, but that physics says should exist. It trains us to think about worlds that blur the categories we've established. It shows us what's possible at the boundaries of our knowledge, because that's where the next discoveries will come from. Not from understanding what we've already seen, but from recognizing possibilities we haven't yet encountered. From building the mental models that let us interpret observations of things we've never imagined. The galaxy is stranger than we know, but it's not stranger than we can know. With patience, with better instruments, with clever mission designs and international cooperation, we'll decode the messages that interstellar visitors carry. We'll learn their stories. We'll trace their origins, and through them, we'll understand our own place in this cosmic web. Every night, telescopes scan the sky. Every image is analyzed, every moving object tracked. Humanity has become a species that watches the spaces between stars, waiting for visitors from the great dark. They're coming. Regularly now, more frequently as our detection systems improve. And we're ready to learn their stories, each one a messenger from another corner of the galaxy. Each one connecting us to the wider universe. Each one proving that we're not alone, not because of intelligent civilizations necessarily, but because the galaxy itself is alive with motion and exchange and connection. The story of 3I Atlas, real or enlarged, to Earth size in our imagination, is ultimately a story about humanity's expanding awareness. We see a speck of light moving against the stars and ask, where did it come from? What is it made of? What does it tell us about the universe? And in asking those questions, we discovered that the universe is stranger, more connected, and more wonderful than we imagined. The real adventure is just beginning. The first chapter in a story that will unfold over centuries. The The moment when humanity realized that the spaces between stars aren't empty, but populated with wanderers carrying messages we're only now learning to read. Welcome to that future. We're living at its threshold, watching as the first messengers arrive, preparing to decode what they tell us about the galaxy we call home. The next visitor is already on its way, somewhere in the darkness between stars, heading toward the light of our sun. We'll spot it eventually. We'll track it. We'll study it. And we'll learn something new about the universe and our place within it, because that's what these visitors do. They teach us, not through intention, but through the simple fact of their existence. They show us that the galaxy is more interconnected than we thought, that chemistry spreads naturally over vast distances, that worlds wander in the darkness, carrying with them the potential for discoveries we haven't yet imagined. And somewhere out there, maybe approaching right now, maybe still millions of years away, there might be an Earth-sized wanderer, a world caught between definitions, a cosmic outlier that will test our understanding and expand our knowledge and show us what's possible when physics pushes to its limits. We'll be ready when it arrives, with better telescopes, better missions, better questions, and with the wonder that drives all science, the recognition that we don't know everything, that mysteries remain, that the universe still holds surprises for those willing to look up and ask, what's out there? What can we learn? What wonders are waiting to be discovered? Those questions don't have final answers. They have next answers. Each discovery leading to new questions. Each mystery solved, revealing deeper mysteries beneath. That's the real gift of interstellar visitors. Not just the data they provide, but the reminder that the universe is knowable, but not yet known. That we're living in a golden age of discovery, where new technologies reveal phenomena our ancestors couldn't have imagined, and that the most amazing discoveries are probably still ahead of us, waiting in the darkness between stars, on trajectories that will eventually bring them into the light where we can see them. Study them and learn from them. The future is written in ice and starlight, and we're learning to read.